Hello everyone. In this presentation, I'm going to present our experimental work on unauthorized drone detection. This work has been authored by myself, Muhammad Asif Khan, along with Hamid Menouar, Usama Muhammad Khalid, and Adnan Abu-Dayya. As we all know, drones have become a commonplace in many different applications, including crowd monitoring and surveillance, in geomapping, in transportation, in recreational and entertainment services. However, we also see that drones can become a potential threat to the society. For instance, a drone being used for crowd surveillance can also be used for tracking people. A drone being used for geomapping can cause severe physical damages to critical facilities. Similarly, a drone being used for transportation surveillance can be used to track vehicle and deploy target attacks. And similarly, recreational drones can be used for privacy exploitation of public. Considering all these potential threats of drones, researchers have been proposing different solutions over the course of time to detect unauthorized drones. We mainly classify the drone detection algorithms into four types: acoustic, RF, radar, and visual-based detection. All these methods have some pros and cons. Considering their intrinsic limitations of each fundamental method, recently there have been sensor fusion-based and authentication-based methods proposed by researchers. In this paper, we are going to investigate the three fundamental approaches, which are acoustic, RF, and visual detection. We could not investigate radar-based detection uh, due to regulatory restrictions. We also propose an advanced and improved method based on RF detection and authentication-based method. So let's start with acoustic detection. Uh, Acoustic detection, as we mentioned before, uses the sound produced by the drones to detect the presence or the identification of the drone. One can usually use a single microphone or an array of microphones to capture the sound signal, which are further analyzed by different methods. Most popular are the recent machine learning and deep learning methods for detecting the sound waves, for detecting the drones using the sound waves. The main advantage of this method is it does not require any line of sight to the drone. However, the disadvantage is that this method is highly susceptible to background noise and it has a shorter detection range. We did some experiments on acoustic detection. We use a 4-mic array, which is connected to a Raspberry Pi processor, which is further extended and connected to Audacity UI. We capture the sound signatures, which you can see on the right-hand side in the figure. So you see here the sound wave with its respective spectrogram. Both of the wave or the spectrogram can be used for detection of the sound waves because they contain the same information depending on the method being applied. We use the first signature of the sound in our system. Uh, sorry, and we extracted the estimated location or the angle of arrival of the drone from its respective signature. And our observation here, as you can also see in this figure, if there were random errors in the estimated location, and it is very obvious that the reason was background noise, which could not be overcome in our experiment. We also did some experiments on the RF detection method. In RF detection, usually the RF signal being used for communication between the drone and its controller is captured using a radio receiver and further analyzed for detection of the drone. The main advantage of this method is it does not require any line of sight like acoustic detection, and unlike acoustic detection, it has a longer detection range. However, the disadvantage is RF detection cannot be used to detect autonomous drones because autonomous drones do not use any communication with the controller. We, we did some experiments to detect drones using the RF method. Here are some experimental configuration settings. We did the experiments in different scenarios, in underground parking, in office corridors, and in outdoor scenarios. The captured RF signature were packed into frames of 4,000 samples long with a sampling frequency of 20 megahertz. And these frames were then further classified to detect the presence or absence of the drone as a binary classification problem. To analyze the performance of the system, here we have shown the performance using a precision recall curve and the AUC or area under the curve plot. And you can see here that the system had achieved a very good result in terms of precision, which is 0.98, in recall, which is 0.94. The value of the AUC or area under the curve was 0.98, which corresponds to a threshold value of 74. So overall, it is a good result. It's a promising for the specific experiment. However, these results might go change when the environment or the circumstances or the drones will be different. So one can see different results in different settings. We then analyze or investigate the visual detection system. In visual detection, we usually use a camera, which can be a CCTV camera, to capture the images of the surrounding. And then these images are further analyzed using deep learning methods to detect the presence of a drone inside the image or the video frame. The main advantage is these methods are usually highly accurate, and this can be extended and scaled up to build a larger system. However, the disadvantage is it requires a line of sight. So if there is no line of sight between the camera and the drone, this method will not work. Another disadvantage is that this system has poor accuracy in harsh environments. So when there is a fog, rain, or dust, the camera, the images captured by the camera will be blurred and not very clear, which will deteriorate the accuracy of the system. We did our experiment on visual detection. We use a PTZ camera to detect to capture the images with NVIDIA Jetson Xavier to run the deep learning model. Different camera settings were being used to capture the environment, the whole environment, and then a data set was built with around 9,000, 10,000 images of drone and around 270 images of helicopter images to train the YOLO V4 classification model. And then this fine-tuned model, which achieved around 90% accuracy on our datasets, was converted to TensorRT and deployed toward the Jetson Xavier processor. And then we use this pre-trained model in our proposed system, where a drone is when a drone is detected using the visual detection method, the estimated location of the drone can be determined from the camera's angle, because the camera angle is known, and based on the camera's FOV, we can estimate at least the location of the drone. And then we can further adjust the camera's angle to track the drone using the bounding box dimension inside the frame. So these methods give us a very good estimation of the drone's presence and location. As we discussed, all of these methods have some intrinsic limitation which cannot be overcome easily. So we propose a novel and improved method based on the encryption and RF detection. So we use the both RSSI values and an encrypted key to detect unauthorized drones. For early detection, we employed RF method, so where each drone in the system send an RF signature, send a frame to the controller. The controller retrieves the RSSI values from the frame, and based on the RSSI values, if it matches to the location of the, if it matches to the drone, which is authorized, it passes the first test, and the drone is detected. And then there is a final detection using the encryption key verification process. So every drone actually generates an encrypted a key, which is further encrypted and transmitted over the air to the controller. The key is generated by using the location information of the drone. So once the drone transmits its key using the Bluetooth interface to the controller uh, verify the key. If both the RSSI and key matches with with those of the authorized drone, the drone is classified as authorized. Otherwise, if any of the tests fail, it is classified as unauthorized drone. So this is one of the limitation. So there is also one limitation of the encryption-based scheme, which is it will not work if the RF-based detection is failed, and mostly, and as we discussed previously, RF detection never works for autonomous drones. So of course, the intrinsic limitation of RF detection we will also face here. Here is some low-level detail of the implementation of these of the encryption-based method, how different frames are being generated and transmitted over the air between the drone, the controller, and the end system for processing. Uh, all right, so yeah, we actually use two drones in our experiments. So one of the drone was configured with all the key generation mechanism, and it was finally classified as authorized drone, while the other one was used for mimicking the unauthorized drone. We use Bluetooth Low Energy for communication between drones and controller, and because of its limited bandwidth of a BLE system, we use a key of adequate size so it can be easily packed in the BLE advertisement packets. Here is the GUI interface, which is showing an authorized drone as green and an unauthorized drone as a red drone. We did this experiment and extended it further into different scenarios, indoor, outdoor, etc. And we almost got 100% accuracy in all scenarios. So this is somehow a very good improvement over the existing scheme, where we can not only detect a drone, I mean the presence of a drone, but also we can use this system to detect an unauthorized drone in a swarm of authorized drones. So yeah, this is promising results and a promising method, I believe. So yeah, we are almost done. So based on all these observation and results of our evaluation and investigations, here are some conclusions. We believe all detection schemes have some pros and cons, and none of them fits all scenarios. So definitely there are trade-offs, and one can choose the right mechanism or the right detection approach based on the particular application. Drone detection is still an emerging area, and we believe if the large data sets are being available over the course of time, the visual detection scheme has the most potential to improve over time with these data sets. Although we can use sensor-based, fusion-based methods to solve the shortcoming of each method and combine the benefits of both, but it will increase the system cost and complexity, which we cannot usually afford in most of the applications. So sensor fusion, although will improve the accuracy, it is not a very good option in different scenarios. And lastly, the encryption-based scheme can definitely improve the accuracy and reliability of the system, so it can be a possible adaptation of such systems. So with this, we end up the presentation, and these are just a few references we use in this presentation. And so it's time to ask questions now. Thank you so much for listening.